And now we go to the third paper in this session, and that will be presented by Nicolas Gama. And the title of his paper is Revisiting Key Decomposition Techniques for FHE, Simpler, Faster, and More Generic. The floor is yours.
Hello. So, yes, I'm going to talk about these new decomposition techniques. Does it work? Okay. So it's a joint work between Sandbox and Infer. And so in this talk, there will be two parts. So in the paper, we did two optimizations about the general arithmetic of FHE. And the first one, we'll talk about external products. And in the second part of the talk, about auxiliary gadgets and bivariate representation. That is an extension of the base 2K representation that is good also in large depth FHE. So let's go for the part one. So yes, so as you know, FHE is based on ring LWE, and from the FHE point of view, actually, FHE was never really about a ring. So when you talk about a ring, you have a multiplicative operation where the two inputs are balanced that you can compose to the infinity. Well, that's not really what's happening. If you look at FHE operation right in the eyes, what you have is actually secret linear combinations, or also known as external products. So things that look like sum of AI, CI, so CI can be a plain text, a ciphertext, or whatever in high precision, and the coefficients of the linear combination will be small integer polynomials, usually. And these external products are really omnipresent in FHE. It covers mathematically every tool, starting from the key switch from 2009, gadget decomposition, relinearization, etc., etc. So it's just that the term external product was not used from the beginning. At the beginning, for example, for key switches, we were more interested in the proxy re-encryption kind of thing, so switching, replacing one key with another one. But if you look at that in terms of external products, we would see that we can rebuild the whole FHE theory, like linear combination with coefficient 0, 1 give the CMUX gate that powers the TFHE bootstrapping. And multiplication with an encryption of the secret key enabled to compute polynomials in S, and that is what is powering the internal products. So depending on whether the space is discrete or continuous, BFV or CKKS. Oops. So yes, external products versus relinearization. So when the internal product, so either BFV or CKKS was first introduced, so there was this operation that was taking two LWE ciphertexts, and first step of the product will give you a type 2 ciphertext, so it's a kind of degree 2 polynomial in the secret key when you have to decrypt it, EFG. And the first method to go from a type 2 ciphertext back to a type 1 ciphertext was relinearization strategy. So basically, it was saying that E times S square looks like a LWE ciphertext that was encrypted with the key S square. So we are going to replace the key S square with S. So that's the relinearization key switch. And later, when we had the external product at hand, another interpretation was that the external product allows us to evaluate the operation multiply by S, and once we have multiply by S, we can evaluate any polynomial in S. So especially a degree 2 polynomial in S, that would be expressed in terms of external product. And that was basically the chimera interpretation of that, except that, well, if we look at the use of external product for this kind of relinearization, the original external product was meant to multiply two secrets. So secret coefficient times secret ciphertext. And the problem is that in relinearization, basically the ciphertext is public, only the coefficient is secret. So if you look at the propagation bright in the eyes, we are just propagating 0 for half of the terms, and we could have erased half of the key for that. So yeah, in the paper, we are just fixing the notation. Instead of having a full secret times secret external product, we can talk about a half external product where we multiply a secret coefficient times a public polynomial. And yeah, of course, so this half external product contains half of the material of the original TRGSW ciphertext and takes half of the time. Now, if you look at it bright in the eyes, I could also call it key switch because it's exactly the same thing. It's just by calling it half GSW, we insist more about the morphism that is applied. So, yeah, for relinearization, it works. And the original external product is just summing together two half external products. So is it just something about syntax? Well, there is something more than that, because now that we have split the external product into two, we can also parameterize the two differently. Yeah. And that's particularly important when we consider the approximate decomposition, because in a LW ciphertext, A has to have more precision than B, the constant term. So this means that in terms of number of FFT, there will be less FFT required to compute the B term. And that has direct impact on the bootstrapping of TFHE. Instead of 8 FFTs per external product, we can reduce it to 7 using exactly the same noise propagation. So yeah, as a result, in FFT, we can expect speed up by 15%. So here are the benchmarks using this possibility. So here on what you would get on a cloud machine, so an N2 standard machine, and here what you would get on a typical laptop with a 12th gen Intel processor, for example. Okay. Now, let's go to the second part of the talk. So the auxiliary gadget and the return of base 2K decomposition. And let's start with an idea that's completely failed in 2018. Well, it started with a failure, but now it's fixed. Yeah, the idea at the beginning was to try to take TFHE blind rotation and try to extend it to do some BFV style arithmetic or CKKS also. And if we look at the external product ciphertext, external product formula, so what we are doing on the ciphertext is gadget decomposition of the ciphertext times something that is fixed, so a fixed GSW key. And if we even decompose it further, so in the arithmetic layer, it means that we are going to do a linear combination of small integer polynomial times a large precision thing. So it can be on the torus or in big integer if you don't like the torus, but I prefer the torus. And here was the big blockers that we have at that time. So we had to do a linear combination where we had a lot of multiplication of small integer things times big precision. And when we have to do such products, we were trying to use FFT. And the problem is that FFT will never take advantage of the fact that one of the coefficients is small. In both cases, we had to compute a high precision FFT to be able to evaluate the product. So that was one of the blockers. And the second blocker is that using just big number representation, the base 2k carry propagation was really prohibitive. So in every operation, we would just spend 99% of the time propagating carries, and that was slowing down everything. So in 2020, basically the idea was that there was a total separation of concern. There was everything that was in small multiplicative depth that would use approximate decomposition with floating points. Well, FP means either floating point or fixed points, whichever is better. And large depth would use CRT plus RNS. And that's it, that would be no crossover, etc. Well, let's, so CRT plus RNS, that corresponds to this beautiful diagram where you have the coefficient space in big numbers and the decomposition of big numbers in the family of primes using CRT. And here from left to right, entity that will deal with coefficients modulo xn plus 1, and on the right, evaluations. So that's a very beautiful rectangle commutative diagram. And I think until last year, everyone thought that it was so perfect, so what could go wrong? I mean, yeah, well, something did go wrong, and it was something I wrote in the first slide. This picture is very good for rings, but unfortunately, FHE was never really about rings. It was about external products. And something that's a paper that was presented last year at this conference remarked was that during this CRT RNS representation, so we had the same external product formula to evaluate, and here there would be one row mod Q1, one row mod Q2, one row mod QL. And to be able to evaluate that using entity, it means that we have to compute L different entities of the same small integer coefficients. So yes, we are computing L entity exactly as if the coefficients were big, which is a bit of a waste. And the idea in the paper that was presented last year is that, well, if mod Q1, mod QL are really annoying, let's just delay them. So we are going to temporarily forget that we are doing a computation on different moduli, and just evaluate this as an integer formula. And then later, much later, once we have the results, we are just going to reduce each row. And now it's much better because we just have a formula that involves small integers. And here we are able to do some DFT with a much lower precision. So yes, that's how they managed to fix the CRT RNS by doing L times less DFTs during the online phase. So yes, mod Q1, mod QL was annoying. Let's delay it to the end and amortize it. And the funny thing with this idea is that it actually also works with base 2K decomposition. And it's exactly the same idea in our paper. So before it was mod Q1, QL that was annoying. Here it's carry propagation. So if we consider huge precision polynomials over the torus and do a base 2k decomposition, we have the different digits or the different limbs that correspond to each power. And when we try to evaluate an external product, we have the same kind of linear combination to evaluate. So the idea is that we can temporarily forget about the carry propagation and do this, well, we have multiple things of that, so that would be a vector matrix multiplication. We have small integer here, so the result will be bounded. That's okay, we can still handle it with small arithmetic. And only once we have the final representation, then we'll propagate carry across the vector. So that's basically the idea of how we can amortize carry propagation. And now, so in order to apply that in practice, so that there are many ways we can do that. The first way is try to be very disciplined, never to propagate carry unless we are explicitly told to do that. And that's a bit dangerous. I mean, when you see this formula, you could always say, yeah, if I take 2 to the k coins of that, it's equivalent to 1 coin of here. And another way of doing that is just to introduce a formal variable y. So 1 over 2k will be y, 1 over 2k will be y squared, etc., etc. So that way we obtain a polynomial in x and y with small coefficients. So that's hence the name bivariate representation. And if we have that representation like that and multiply it with a polynomial in x, well, obviously there will never be any mix. Each power of y will be treated independently, so that means effectively there will be no carry propagation. So one advantage here is we're just replacing carry propagation with polynomial arithmetic. But then if you look at that, we now have bivariate polynomials in x and y with integer coefficients. So you would say, yeah, but now I could take a polynomial like that and multiply it with another bivariate polynomial. And that can seem a bit strange at the beginning, because here we were on the torus. In the torus, we don't take 2 torus elements and multiply it together. Doesn't make sense. But for some reason, here it seems to make sense. And there is actually a reason. It's because there is a genuine morphism between lifts over the real space and the bivariate representation. And it turns out that this morphism about lifts, multiplication between lift, is exactly the one used in BFV and CKKS internal products. So in some sense, we can hit 2 birds with 1 stone using this bivariate representation. But there is something even more. Now that you are in a polynomial arithmetic, if you want to do some fast arithmetic, you can do not only DFT over x, but also over y. And people who are familiar with a big number Schoenager-Strachan algorithm will already be familiar with this kind of techniques. So there is a fast arithmetic for addition and multiplication over the bivariate fields. So we are actually hitting 3 birds with 1 stone. So yes, there are lots of advantage of using this kind of bivariate representation. So anything that is external products are faster and easier and more natural on base 2k. We have also a compatibility with the internal products, as we saw before, since we can multiply bivariate polynomial. The prefix property, so rescaling is absolutely free. It's completely free under this representation. It just corresponds to a truncation of the bits. Parametrization, so in base 2K, everything follows directly from the noise. There is no such thing as additional modulus for CRT. We just have the noise level, and based on that, a linear law that says how many terms we need to have. And something also, it's in the CKKA noise levels, so they are now continuous, the same as BFV. And for those who know, there was a slight difference between how the noise worked for CKKS and BFV. In CKKS, in the CRT representation, we always have to artificially rescale CKKS ciphertext before doing a product so that it fits to an exact boundary between the primes. And the problem does not happen if we have a base 2K representation. So there is just a minor setback. So one of the negligible terms in the complexity of a product are a little bit larger with the bivariate representation, but luckily the dominant complexity term are improved. So overall, I'd say it's good enough. So yes, before we had a complete separation between RNS representation for large depth and TFHE style approximate decomposition for low depth. With this work, we were able to prove that actually every combination, so CRT with entity, CRT with FFT, bivariate with entity, and bivariate with FFT are equally valid to represent actually any depth, and also any conversion between these representations are also fast. One of the implications is about the basically an arithmetic API that covers all the operations. So what do we expect about an arithmetic API that has a hardware backend? So first, on the hardware level, I would say don't let you be tricked by machine learning that says that half precision floats are enough. Here we should have reasonable precision, so something like between double precision and quad precision. It doesn't need to be float. It can also be integer. It can power entity or FFT. That will be, the performance will be equivalent. But yeah, the main three operations that are important is first, of course, DFT, IDFT. And about the arithmetic, we have either, so the library should work over vectors of small integer polynomial. And ideally, we would have convolution of two vectors, so convolution products, or vector matrix multiplication, where the matrix can be preprocessed. So the matrix usually only depends on key material, so it's generated at keygen, and it can be preprocessed to have any form that makes the product efficient during the online phase. And basically, if we have these three operations, we have a library that is omnipotent. We can power efficiently any CRT and bivariate front-end for any depth and achieve blind rotate, products, key switches, everything very efficiently. Yeah. So I'd say this API looks to me like a sufficient target for hardware developers. Much easier than a full-fledged CRT RNS API. So yes, we are currently developing a speculative arithmetic proof of concept that will be a software implementation that achieve this, and we plan to do a demo maybe in a few months. Probably by Eurocrypt. So yes, currently if we do a pure software single core implementation of this library, this is the kind of performance that we obtain for key switch automorphism and CKKS products. So that would be a level 30, multiplication level 30. So this number of bits for the precision. Yeah, basically key switch and products would be like 0.2 seconds. So much better than what the original full RNS were providing, and comparable to what the former paper at Crypto last year provided also. And yeah, that concludes the talk. Yeah, this is just conclusion and key takeaway. So a summary of what we already said. So thank you very much for listening.
Thank you. Any questions? Must be some questions.
Thank you for the talk. Is there any significant or noticeable difference with the noise in the two products?
For the noise propagation, no, it's exactly the same.
Okay.
Here.
For the entity, the timings are given with UINT 128, or is it like, because I see it's 128 something entity, so I assume it's the size of the integer?
No, so for this entity, we used 4 64 bits
primes
integer. So the prime, no, 4 32 bits prime, and we were using 64-bit arithmetic to be able to do multiplication.
Ah, okay. Okay, so you have to convert the value to a CRT domain. Okay, and
Yes.
it's still faster than FHE.
Yes.
Okay.
Thank you. We have more questions. 128-bit arithmetic. Let's thank the speaker again.